Hello, my name is Matthew Payton and welcome to my NMBR142 Assessment Task 2 video presentation on the application of geometry. In this assessment we are looking at circle geometry and I'll explore the relationship and patterns of equidistant points of a circle and look for some generalizations. The first thing I decided to do was to work out what equidistant angles I needed for all of the points on the circle from 2 to 9 so that I could create these circles in GeoGebra. I'll quickly show you how I created these circles through GeoGebra. So if we enter in GeoGebra and create a circle as such, we are then going to add in some angles with given sizes. Now to start with, I'm going to do the circle with 2 points. To do that, I'm going to create another point in here with an angle of 180 degrees. That will give me 2 points around the circle of equidistance from the center and from each other as well. Now for aesthetic purposes, I like to take the angle some away from the middle and I'll rename the points as well to A and B. Okay, so to start our circles, I'm now going to create a segment. So starting with 2 points, gap of 1 is a straight to the B, and then another gap of 1 would take us back to the starting point. So our first circle created would be 2 points, gap of 1, and I haven't had to take my pen off the paper to create that line, that segment. It's also resulted in a diameter being drawn. Now for this assessment we're going to use the arrangement of X, Y, Z, for X being the points, Y being the gaps, and Z being the amount of times our pen has had to leave the page in this formula here, this arrangement. So for our first circle, our arrangement will be 2, 1, 1, where 2 is the amount of points, 1 was the gap we used, and we only had to put our pen down once. Alright, so for my second circle, we're looking at 2 points, gap of 2, and we'll see how many times we have to pick our pen off the paper. So if I start with the A, that's a gap of 1, we'd come all the way around, we're back to the start again. So it'll be left as a single dot. We would then move to our B, we've got a gap of 1, back down to a gap of 2, and we're back. There's no chords drawn on this diagram, on this circle. So to keep track, I have created a table, which you can see it started there. I've actually completed the table here, and as you can see on the left hand side we have the number of points, the gap which is the Y, and the amount of times we've picked up the pen in the Z, creating these arrangements as such. I've also kept track of what shapes are created when completing these circles. As you can see in this document, this is a complete arrangement of circles done in this assessment. So here we have 2 points on the circle. When we get to the 3 points on the circle, we're starting with A here, gap of 1, drawing even chords to create an equilateral triangle. You'll notice that that's also recreated in our gap of 2. So if I start on the A, gap of 1 there, gap of 2 would create that line between A and C. Then gap of 2 from C would go back to B, creating that line. And then a gap of 2 from B would be going back to A, creating the other line. So we're creating 2 equilateral triangles, but in different ways. And for gap of 3, we're back to the no chords created. With 4 points on the circle, our first shape is a square. Noting that all the side lengths, or the chord lengths, and the angles are the same on a square, so it's creating a regular polygon. For our gap of 2, we've created 2 different diameters that are meeting at a perpendicular point in the middle. Our gap of 3 recreates the square, going the opposite way, and our gap of 4 creates the no chords again. With 5 points on the circle, as you can see, it's creating a pentagon into a 5-sided star, recreating the pentagon, and into no chords as well. For our 6 points on the circle, creates a hexagon. Then we're into a hexagram. Looking at a lot of diameters, and scrolling through 7 with the heptagon, hexagrams, range of different hexagrams, and back down to the no chords. 8 creates octagons, octograms, and so on, and 9 with the nonagons. Okay, so all circles are created there. Into the complete table, as you can see with the arrangements, all possibilities have been explored, and you'll notice where the shapes are here, there's a lot of repetition between the shapes created all the way through enneagrams for the 9 points on the circle. And interesting to note that at all points, when there's a gap that equals the number of points, it creates no chords. From this point, I decided to have a bit of a closer look, and I made my table a little bit more succinct. And as you can see here, we've got the arrangement at the top here, where x is equal to the number of points on the circle, y is equal to the gaps that we're taking, and z is to the amount of times we've lifted our pens. By arranging it this way, you start to see some patterns in the numbers, and then down the bottom here I've got some key observations. So the first one that came to mind was when the gap equaled 1, the amount of times you lifted your pen also equaled 1. So if I look at this in an example, look at our 9s here, when our gap was 1, it created one shape. Alright, and we only had to lift our pen once. Also creating, with the gap of 1, created a regular polygon every time, where the number of sides was equal to the number of points on the circle. Regular polygons meaning that they have the same length, same angle. Okay. Second thing I noticed was when when the number of points equaled y. So, for example, here you've got 2 and 2, 3 and 3, 4 and 4. Then the z, the amount of times lifted off the pen, was also equal to that same number. So it's a last in the arrangement, last in the sequence. Alright, so as an example, we have our 9s with no chords, we have our 8s with no chords, our 7s, so gaps of 7, 7 points, creating 7 times lifted off the page. That led into when I'm comparing, so in this table, when I noticed a lot of the shapes were reoccurring, and as an examples, we're looking at, so for example, the arrangement of 721 and 751, I found that whenever the y was equal to the x, so when you sum the two y's together, so your 5 and 2 was equal to the x, which was 7, they would create the same or congruent shapes. So for example, with 6, we've got a y of 4 and a y of 2, creating the same shapes. A y of 1 and a y of 5, making up the 6, creating the same shapes. So as a rule, I decided that if y plus y equals x, then the shapes were going to be congruent. The next thing I found was that when x is a prime number, so your primes here of 2, 3, 5, 7, then all of the z's, all of the amount of times you're lifting the pen off the paper was 1, except for the last one in the arrangement. Alright, so for example with 5, you've got your z as 1 all the way through until your last arrangement, which is equal to the x. Same with the 7s. Now, it works with primes because they don't have any other factors except for themselves and 1, which leads us into the overall generalization, which I found, which to find your z, to find your amount of times lifted off the paper, what you need to do is find the greatest common factor of your x and your y. Okay, so your z will be the greatest common factor of x and y. As an example, I'm going to look at this one, with the arrangement of 8, 6, 2. So I'll find that as an image. That would be this image here, 8, 6, 2. So I need to find the greatest common factor between the 8 and the 6. Now to do that, you create some prime factorization or your factor trees. So prime factorization of 8, you split that into factors of 4 and 2, and your 4 gets reduced again to 2 and 2. So 8 has prime factors of 2, 2 and 2. 6 is split into 3 and 2, with prime factors of 3 and 2. Now the only common prime factor that exists between the two numbers is 2. So if we go back to our table here, you'll find that the z is the greatest common factor, which is 2. Now this works for all of them, so that is why I've made that the general rule for this assessment. Thank you for listening, and I hope you have a fantastic day.